Greetings students, my name is Aziz Alam. I did my graduation in Applied Physics from IIT Roorkee and I have been associated with askIITians for the past 4 years. In this video lecture, we will learn about current electricity. Now in current electricity, we will learn about what exactly is current electricity and what are the different parameters which affect current electricity, that is both internal and external to the conductor which carries current electricity. Then, moving on to the next part of the current electricity, we will learn about one of the most important circuit elements, that is resistance. Again, in this particular head, we will learn about the factors affecting resistance, both external and internal to it. Then, moving on, we will learn about the power sources which drives the current in the circuit. Then, in the later half of that topic, we will learn about the combinations which are available with the cells and the resistance.
So let's start off with the first topic of discussion in the chapter of current electricity, that is, definition of electric current. Electric current is defined as the charge flowing through any section of the conductor in 1 second. Current I is given as Q by T if the rate of flow of charge is steady. I is equal to dQ by dt if the rate of flow of charge varies with time. To get a better hold of what these mathematical expressions mean, we'll put up with a diagram. So this is the part of a conductor and this is the cross section of interest, and this is the direction along which the charges are flowing. If equal amount of charges flow across this cross section in equal intervals of time, then current is equal to Q by T. The flow is uniform. If unequal amount of charges flow across this cross section in equal intervals of time, then we need to put up with the differential expression of current, that is I equals to dQ by dt. So depending upon the situation where we need to either use the expression for uniform flow of charges or non-uniform flow of charges. So this is in relation to the definition of electric current, the mathematical expression corresponding to it, and what exactly do the mathematical expression mean in physical sense. So now we'll shift our attention to the different types of current which we observe in nature or which we observe in our day-to-day life. So we'll put up with a graph of current in y-axis and time t in along x-axis. So first up, it's the steady current. So steady current is also known as DC, the direct current. The property of direct current is its magnitude remains constant throughout the time. It doesn't vary with the time. So hence the name DC. The next up is when the current varies linearly with time and when current is a function of, or let's say a random function of time. So these two are quite rare to us because these two are only used for research purposes. So they have some specific use or rare uses. So we don't observe these two types of current in our day-to-day life. So next up is alternating current, one of the most famous types of current. So this is the same current which we have in our household circuits. So alternating current is basically current starting from some random value, reaching its maximum value over here, then falling down to its minimum value in the same direction, that is 0, and then changing its direction and increasing the magnitude of current along that direction and again reaching a maximum value in the reverse direction. Now it does the same thing after reaching the maximum value. It decreases to a value of 0 in the reverse direction, then it again increases to its maximum value over here, and it does that repetitively. So hence it's an alternating current. It increases, falls to 0, then changes its direction, then again increases, falls to 0, then again changes its direction, and it does that repetitively. So hence alternating current. So these are the types of current which we observe around us or which we use. So now we'll shift our attention to conventional current, under which we will study about the direction of the current. So the direction of the current is the direction along the direction of motion of positive charge under the action of electric field. So this is the convention which has been said, that is, we need to consider the direction of current as the same direction as a movement of positive charge. What about movement of electrons? The movement of electrons are just in the opposite direction of the current. So that's the convention which has been set out, and we need to follow it throughout the chapter. So for a graphical representation, let's say here I have a positive plate, here I have a negative plate. So positive charges are flowing from this plate to this plate, hence the direction of the current is the same direction as that of the movement of positive charges. Here I have a negative plate, here I have a positive plate. The electrons are flowing from negative to positive, and the direction of the current is just the opposite of that of the movement of electrons. So just keep in mind that we need to follow these two conventions. Direction of movement of positive charge is same as the direction of current. Direction of movement of negative charge is just the opposite of the direction of current. Now we study about drift velocity, that is, what is drift velocity, what are the factors affecting drift velocity, and what's the relationship between drift velocity and the current. So these are the three expressions, that is, the first two actually tells me the information about drift velocity. The third one tells me about the relationship between the current and drift velocity. So these are the meanings of the symbols used in these three expressions. So we will come back to these expressions later, but we'll first get clear with the setup. So I have this conductor and his cross section is A. I'm connecting this conductor to a cell to the wires. So I have electric field set up inside it. So electrons will try to move in this direction, and the current gets set up in opposite direction, and this is the length of the conductor. Now we want to find out what exactly is the drift velocity and the relationship between the current and the drift velocity. For that, we need to get hold of this, that is the relaxation time. So relaxation time is basically the time between two successive collisions of an electron. So basically, when electron moves inside a conductor, it collides with either with the other electrons or with the atoms. So the time between these types of collision, two successive collision, is known as the relaxation time. So let's say Vd is the average velocity between those two successive collisions, and the time t between those two successive collisions is known as the relaxation time. So if I divide my average velocity between those two events by the time between those two events, I will get an average acceleration. That average acceleration is equal to the force applied on that particle divided by its mass. So we know that the force applied by electric field on electric charge is charge times electric field. So dividing that force by its mass, I will get the average acceleration. So hence we have found out the expression, or let's say the value of drift velocity in terms of electric field and relaxation time. Now we need to find out the relationship between the current and the drift velocity. We know that the amount of volume that is being covered by the charge in 1 second is equal to A times Vd, because Vd is the length it covers in 1 second. Multiply this by the number of electrons per unit volume, I get the number of electrons per unit volume. Multiplied by the volume gives me the number of electrons in that particular volume. Multiplying it by the unit charge that an electron carries gives me the total amount of charge which flows across a cross section in per unit time. So I'll write it over per unit time, which is none other than the current. So I finally end up having the expression of current in terms of drift velocity, that is NEAVD, the same as we got here. So hence we have found out the relationship between the current and the drift velocity. So we'll now try to shift our attention to current density. So current density at a point within a conductor is the current through a unit area of the conductor around that point, provided the area is perpendicular to the direction of the flow at that point. So current density is basically current per unit area, and its vector form is given by this: I is equal to J dot A, and the formula corresponding to current density in terms of the number density, the electronic charge and drift velocity is this: J is equal to NEVD. Now let's try out an example corresponding to the concepts which we have learned till now. So the question states the magnitude of J of the current density in a certain lab wire with a circular wire cross section of radius r equals to 2 mm is given by J 3.00 into 10 to the power 8 into r square, with J in amperes per square meter and distance in meter. What is the current through the outer section bounded by r equals to 0.900 r and small r equals to r? We cannot use the expression which we have, that is I equals to J vector dot A vector, because of the fact J is varying in nature. So we'll use the differential form of the current, that is I is equal to J dot dA, and the limits are given, right? So for the first limit is this, that is 0.900 r, and the final limit is r is equal to capital R. So if we substitute the values of J over here, so let's say 3 into 10 to the power 8 be denoted by K, and so it's K R square. The differential area is 2 pi R dr. If we integrate it from 0.9 R to R, we'll end up getting 2.59 milliampere. Because of the fact that integration gives us K r to the power 4, 2 pi outside divided by 4. If we substitute the values corresponding to the limit, that is first and second, we'll end up having 2.59 milliampere. So let's move on to the next example. It says a copper wire of diameter 1.02 mm carries a current of 1.7 ampere. Find the drift velocity of electrons in the wire. Given N, the number density of electrons in copper is 8.5 into 10 to the power 28 per meter cube. We know that current is equal to NEAVD, where N is the number density, E is the charge of the electron, A is the area, and VD is the drift velocity. So we have the diameter over here, so this gives me an idea about the area. We have the current also, so I have the current. We also have the information about N, and we already know E. So we just need to find out the drift velocity, which can be easily found out using I divided by NEA. So if we substitute the different values, we will end up getting 1.5 millimeter per second. So if you actually observe this, the drift velocity of electrons is very, very slow.
So we just concluded the first part of current electricity. We defined what is electric current. We also came to know about the direction of electric current, and we studied about the factors affecting current electricity, that is drift velocity and current density. Now we will shift our attention to one of the most important circuit element, that is a resistor. So stay tuned for the upcoming part.